So today we're going to be looking at something called stable and unstable nuclei and how these can lead on to something called decay. Different nuclei have different numbers of protons and neutrons. So let's say this graph depicted all possible nuclei with a different number of neutrons or protons. So an example nucleus, like say a point here, could have 40 protons and 35 neutrons. Now I've drawn in the y equals x line there, which basically means that any element that lies on this line would have the same number of protons as neutrons. So if this had 35 protons, it would also have 35 neutrons. Now this red line that I've drawn in here is known as something called the line of stability. Now most elements or nuclei lie on the line of stability. And this means that they are therefore stable nuclei or elements. Now you can see here that this line of stability follows the y equals x line up until 20 neutrons and 20 protons, and then it sort of curves upwards. And this means that for smaller nuclei, or nuclei with less than or equal to 20 protons, they are stable when the number of protons is equal to the number of neutrons. However, larger nuclei, which have a proton number greater than 20, are more stable when there are more neutrons than there are protons. And if you remember back to your particle physics chapter, this is because there needs to be a balance between the strong force and the electromagnetic force. Now, as I said earlier, this graph depicts all possible nuclei. So we could have nuclei that are unstable in these sort of areas on the graph, where these here are all forms of unstable nuclei. Unstable nuclei can go on to gain or lose protons or neutrons in order to become stable. This process here is known as radioactive decay. Now there are two main properties of radioactive decay that you need to know, and you need to know what these terms mean. Let's say we have these bunch of nuclei or particles, and the one in circles are new particles, and the other ones are old particles. Now these are the same exact type of nuclei or particles. It's just that the ones that are circles have been formed more recently. Now the first term that you need to know what it means is random. And this means that it's not possible to determine when and which particles will undergo decay. So that means even these older particles are not more likely or less likely to decay than these newer particles. It is simply not possible to determine which of these individual particles are going to decay next, and when exactly in the period of time they will decay. Now, a second definition of decay that you need to know is called spontaneous. And spontaneous decay is that decay which is not influenced by external factors. This means that there is nothing that I can do to a bunch of particles that can affect how or when it will decay. Now, there are 3 or 4 main types of decay that you need to know, with that being alpha decay, beta plus decay, beta minus decay, and gamma decay. So let's start with alpha decay. Now, an alpha particle is basically a helium nucleus. So this is a nucleus with 2 protons and 2 neutrons. So let's say we have this element X with 92 protons and 135 as its atomic number. Now, if this were to undergo alpha decay and produce a helium nucleus, this means that the atomic number will decrease by 4, and the proton number will decrease by 2 and it will produce this element Y. So element X will lose 2 protons and 2 neutrons. So if we look at our graph of nuclei with a certain number of protons and a certain number of neutrons, if element X was there and it were to lose 2 neutrons and then lose 2 protons, it would decay into this stable element Y, which lies on the line of stability. So this line here would represent the decay of this element. Now beta minus decay, or this beta minus particle, is literally the emission of an electron. Let's say we had this element M with a atomic number of 92 and a proton number of 34. If this were to undergo beta minus decay, it would form this element N with a atomic number of 92 and a proton number of 35, whilst emitting this beta minus particle. Now what scientists and researchers were able to do was they were able to measure the kinetic energy of these beta minus particles that were emitted. So they found out that there was a range of kinetic energies that different beta particles occupied, and this here is a number of beta minus particles at that specific kinetic energy. With this data, they were clearly able to see that the kinetic energy of the beta minus particles varied. Now, because of this range of kinetic energies, this meant that this decay equation could not be true, as energy is not conserved, which means that another particle must also have been emitted. As we know from our particle physics, this here in this case is our anti-electron neutrino. And if you were to look at your charge, your baryon number and your lepton number, you can now see that this equation is complete. Now in general, the beta minus decay is simply a transformation of a neutron into a proton. So our beta minus decay looks something like this. We have a neutron transforming into a proton and an electron or a beta minus particle with our anti-electron neutrino. And if you were to check your charge, your baryon number and your lepton number, we can see that these are all conserved. Charge on the neutron is 0, proton is +1, electron is -1. Anti-electron neutrino is 0. Our baryon number on our neutron and our proton are both 1, and they are both 0 on the beta minus particle and the anti-electron neutrino. And our lepton number for our neutron and proton are both 0, and they are +1 for our electron and -1 for our anti-electron neutrino. We had element M here with 34 neutrons and 58 neutrons. It would lose 1 neutron and gain 1 proton to form element N. And element N would have a proton number of 35 and a neutron number of 57. So in this case, this red line here would depict the decay for beta minus decay. Now beta plus decay is basically the emission of a positron, which, if we remember, is the antiparticle of the electron. And this here is basically the opposite of beta minus decay. Here, a proton is getting converted into a neutron. Let's say we had element A with a atomic number of 90 and a proton number of 29. This undergoes beta plus decay. It will form element B with a proton number of 28, atomic number of 90, a beta plus particle, and a electron neutrino. Now the general case is basically just a proton getting converted into a neutron plus a beta plus particle plus a electron neutrino. And again, if you did the charge, baryon number, lepton number, you should see that they are all conserved again. Now in this case, element A would lose 1 proton and gain 1 neutron to form element B. And element B would have a proton number of 28 and a neutron number of 62. And that line there represents our beta plus decay. Now what you need to understand is all these types of decays will try and get a particle, such as particle A in this case, to move closer towards the line of stability, and will always try to eventually end up as a stable element.
Now the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.